Thank you very much for joining us in this session on hydrogen. Please come in, you're very welcome. So we've got 3 talks today on a range of aspects of hydrogen. So we'll be journeying into how it's produced, how we can utilise waste products, although from whiskey, zero waste, and we'll be looking at hydrogen in the subsurface, so a real journey through all of the aspects of hydrogen. So really looking forward to hearing all your talks. Thank you. So the way we're going to run the session is you'll each give your talks, and then we'll do questions after your talks so that you can just stay up. So what we'll do is you'll come up to the podium, do your presentation, and then we'll take questions from the audience, and we'll just break you up into those sections. And then if there's time and the inclination afterwards, we can have a more wide-ranging discussion on hydrogen and how we all fit and see that working into our research. So yeah, it's my pleasure to welcome you to the session on hydrogen. And first up, we have Hai-Chan. Hai-Chan Chen is going to talk to us about the utilisation... No, sorry, he's not. He's going to talk to us about the development of carbon-based catalysts for upgrading biogas to low-carbon fuels. So come up, don't trip. Oh, yes,
well.
Stephen.
You're limited to 10 minutes, be very strict, okay? 10 minutes we will stop you because we have to move on.
10 minutes.
The other thing is that of the 3 of you, remember that there is a prize for whoever Kerosene deems is the best presentation. Isn't that right?
Yes, it is. So there you go.
Hi everyone, my name is Hai-Chan Chen, and I'm from University of Strathclyde, Chemical and Process Engineering. And today, my topic will be development of carbon-based catalyst for upgrading biogas to low-carbon fuels. So, in my presentation, I will spread the 2 background, research gap, and objectives and measures, and results, conclusions, and then is some future work plan. So, in these days, global warming is a very important question, which is caused by greenhouse gas. And also, UK have a high yield of biogas production, which for biogas, it can be used to replace the statement of fossil fuels and can meet the carbon neutrality. In 2015, renewable energy investment in the UK has reached about 0.8% of GDP, and it will be expected to rise in the few decades. Also, competitive hydrogen production technology is required to upgrade the efficiency of produced hydrogen. So we can see in this picture, in Scotland, it has a large ability to produce biomass. It's about 12,000 meter per hour. That's, if we use that, it can save a lot of fuels and can have benefits to consumption CO2. Okay. So for now, the technology for use biomass, there are 4 main methods. The first is dry reforming. The second is steam reforming, partial oxidation, and autothermal reforming. For steam reforming, it needs high temperature and need a lot of steam. For partial oxidation, it needs high temperature and high pressure. For the autothermal reforming, it needs very high temperature, and we cannot control the extra production. So we choose for dry reforming. Dry reforming is a reactor from methane and CO2. Methane and CO2, they dissociate in the material of catalyst and then recombine to form CO and hydrogen. And in the red is the 5 main reaction in dry reforming process. The first is what we want, and the third and the force is what we want to prevent to happen. And this is the research challenging in recent research. The first is missing activation. The second is thermodynamics and kinetics. And the third, what is important, is catalyst development to inhibit carbon deposition. And the fourth is plastic reaction suppression. So my objective is to develop a carbon-based catalyst which has the usage of carbon resistance in dry reforming. So the first of the catalyst, what we want is it can operate at low temperature, and the second will be suitable for reforming in microwave assisted state, which is selective to microwave, and it will supported by carbon-based from biomass gasification waste. And then my objective is determine the effect of processing conditions on catalyst preparations, and then to characteristics and test the catalyst. So this is the structure I chose for the metal of the catalyst, because noble metal catalyst is very expensive, so that cannot be used in industry. But perovskite structure is researched to provide that have the similar ability like noble metal. So I choose the nickel, tin, cesium, and the titanium, which can have the ability to catalytic the reforming and also can resist the carbon deposition. So this is the process of me to catalyst the synthesis. The first is prepare for char and prepare for solution, then log in the solution to the char and drying the char. At last, to roast the catalyst. So I got 3 samples, and I doing some characterization of them. So this is the result of PET and size. The first 3 is my result, is the result of my sample, and the last 2 is compared with some others who also use biomass to produce carbon-based catalyst. That can find my catalyst surface area is about 271 to 321 meter per gram. It's much more than some the others. Also, this is the XDR and SEM results. So we can, from the result, we can see crystal structure changes with consumption of the solutions. And also from the SEM, we can see visible crystal, it's spread in the surface of the char. And then I use an Aspen Plus to make a simulation for the dry reforming process. I use the Egypt's reaction and assume there is no carbon deposition happens. So I find the suitable temperature for dry reforming is from about 750 degrees C to 850 degrees C. And also that can meet the TGA result. For my catalyst, it can survive on about 900 degrees C, which can meet the reaction temperature in the simulation. So for the conclusion is that my catalyst, it has high surface area and It's similarly stable and usable in reforming temperature range for dry reforming. Also, the prone structure of the catalyst can accommodate the methane and CO2 reaction, which from biogas. And the provescate path attended in catalyst structure, and we can see it will have good catalytic activity. So the future work is use this catalyst to doing some catalytic reforming operations, and then I want to doing some experiment with wood char. Yes, use wood char as a support for the catalyst, and then I plan to use a microwave as a heating device to change the traditional tube furnace to doing some experiment to test the catalyst in ability in microwave state. So that's all for my presentation.
Thank you, and that's really fascinating talk. I love all of the circularity about what you're doing, actually, when you start to think about the whole process. And it's great that you're thinking about the catalyst supply and trying to find alternatives for that. So thank you. Any questions from the audience? Anybody working in this? Yeah, please do.
So I'm just going to ask, a bit curious, for the hydrogen you produce,
Yep.
what color of hydrogen, I mean, what color code, I mean, based on the hydrogen color code, what color does it fall? Is it the green hydrogen or the blue hydrogen, or maybe pink?
A new color.
It should be green hydrogen because it's from biogas, so it can It's from the biogas. So in UK, there are some factories. They can produce biogas from like some waste from the kitchen factory, the coal factory. From the waste, they can use them to produce biogas. I think that could be assumed as green hydrogen.
Okay, all right. So, but the source of the biogas contains methane, right?
Yeah.
And methane in itself is has some kind of what is it called? It's also an emitting or a greenhouse gas. It's a greenhouse gas, and so if you produce the hydrogen from biogas that has potentially methane, so. Because the argument is that for green hydrogen is basically
you can say from
pure
from
green.
This one in biogas the composition of CO2 is more than CO2, right? But for dry reforming process, the feedstock of methane and CO2 it should be one. The rate of them should be 1. So when we use biogas to produce hydrogen, the CO2 from biogas is not enough, so we can consumption the CO2 from the air, which can reduce the greenhouse gas.
So where does the CO2 goes to? Where does the CO2 in the biogas? I mean, because this is more like your feedstock.
No, this is the composition of biogas.
Yeah, which is basically going to serve as your feedstock in the hydrogen production, right? So where does the CO2 goes? I don't know if you. What I'm saying is, I just want to know the category that because the understanding behind green hydrogen is that you generally don't have any, potentially you don't have any form of any gas that falls under the classification of greenhouse gas, but your feedstock, which is a biogas, potentially has, from what you're showing, it has a methane. Methane itself is also a dangerous gas. I mean, dangerous greenhouse gas. It has CO2 itself. Again, we don't know where it's going to go, but I assume it's going to go somewhere. So the hydrogen you produce from this process, does it also do we see it as a green hydrogen or blue hydrogen, or you want to give it another color code, which is possible, it's something you can do? I'm just curious. It's not to put you under any pressure.
It's an interesting debate because, the argument, I guess, is that the biogas in the first instance is saving emissions. So because you're creating it from organic material, theoretically, that material should have absorbed some of the CO2. And we were just discussing this earlier on, actually, about that circle. It might be net, but it's not zero because you've brought some CO2. You've taken your CO2 out of the atmosphere into your your organic material, and then you convert it to the biogas, and then of course you're going to burn it, and it's going to put the CO2 back in the atmosphere. But you've taken some out at the beginning rather than. So it's might need a new colour, pale blue.
I want to also contribute here because from the title of his work, he said a carbon-based catalyst.
Yeah.
So I think if you're using carbon-based catalyst, there is high percentage of the CO2 itself being absorbed into the catalyst again, not
Yep.
released to the atmosphere.
Yeah.
So possibly we're still looking at maybe hydrogen
Yeah.
being produced.
Yeah, I think there's some nice circles of carbon capture and release.
What about the methane? What about the methane?
It's reformers. What was
Split. Methane's smashed. Thank you. Excellent questions and a really nice discussion. Thank you. I think I need to come back onto the lectern. Okay, thank you very much. That was really an interesting talk. Robert, you are up next. So Robert's from the University of Strathclyde, and he's going to talk about the utilisation of distillery whisky waste streams. So again, feeding onto that sort of that bio organic material as feedstocks for hydrogen production. So that's lovely. It's continuing the theme. So thank you. Thanks, Robert.
Thank you very much for the introduction. And good afternoon, everybody. Thanks for sticking around for this talk. So I am a KTP associate between University of Strathclyde and R&B Distillers, and I'm going to update you on our progress in terms of converting some whisky distillery wastes into hydrogen via electrolysis of biomass. So I will give you a bit of an introduction to the overall KTP project, as well as R&B Distillers Limited. We'll then go over the aims and objectives, look at some energy and waste stream audits from the distillery, and I'll give you a brief introduction to the biomass electrolysis process before wrapping up. So, I don't have a pointer, I don't think, but a knowledge transfer partnership is essentially a project between a knowledge-based partner, which in this case is the University of Strathclyde in Glasgow, in the red, and a commercial partner, who is the Isle of Raasay Distillery, or R&B Distillers, which is located just off the east coast of the Isle of Skye in Scotland. And the overall project is designed to sort of take some of the aspects that may be in an academic laboratory and transfer them to the commercial partner for some kind of gain for them. So we're looking at electrochemical engineering processes for clean hydrogen production in this case. And my role is, as a KTP associate, to be a decarbonisation distillery engineer. So R&B Distillers, or Raasay and Borders Distillers, it is an artisanal distiller of gin and whiskey. They opened their first distillery on the Isle of Raasay in 2017, and that's what you can see in the pictures here. Nice new visitor centre, which was in the gold, which was finished this summer. And on a clear day, if it's not raining, you can see the cooling on Skye from the still house there. They employ about 30 staff on the island, and they also blend whisky called Tweeddale down in the Borders, and have plans to open a new distillery about 2.5 times the size in Matrahanish and Campbelltown. So in terms of a project overview, it's going to be quite a high level one for this talk. There's quite a few different facets of it. Distillation is obviously a very highly energy intensive process, and it's typically fueled by red diesel or kerosene, which has significant CO2 emissions associated with it, even at the small scales of the Raasay distillery, which is less than 200 litres of pure alcohol per year. And they wish to essentially decarbonise the whisky and gin distillation process in a holistic manner so that it fits in with the needs of the community of 160 people on the island, to reduce their environmental impact and sort of improve the sustainability of the business as well. So my job is to essentially provide a comprehensive study of the energy footprint of the distillery, the waste and water streams, and what technologies we could use to replace the current kerosene-fed boiler. And I'll brief you at the end of this presentation on the biomass electrolysis process we're using to produce hydrogen from solid and liquid biomass wastes of the distillation process. So we'll jump straight into the energy audit. Obviously there's a lot of math behind this and a lot of metering of fuels used. I'm mainly going to concentrate on the kerosene, which feeds the actual distillation process, and that's just combusted in a large boiler. We also have LPG for heating of the visitor centre on site, and we have electricity as well, site-wide. So looking at the kerosene usage, we have 1.6 million kilowatt hours of annual energy demand just to provide steam for the stills and the mashing process, for example. We also have some values that were reported by Zero Waste Scotland a few years ago to report them to. As you can see, the values that we've predicted on the left-hand side are slightly larger than theirs for the kerosene usage. That may be because their values don't include things like cleaning cycles and things like that. In terms of the annual predicted emissions, in tons of CO2 equivalent, that also includes the associated emissions of methane and NOx. We're just over 420 tons. And the main deviation between our values and the Zero Waste Scotland values primarily come because of the difference in predicted annual energy usage we've calculated, but also their calculations were done using red diesel. Now, back in March, the government hiked the duty on red diesel, so they switched to kerosene at the distillery because it had no duty and no climate change levy attached to it whatsoever. So much, much cheaper from a business point of view, but we're looking at over 500 tonnes of all the fuels combined of CO2 emissions per year. The graph on the left, if we look at a bit of an assessment of how we could replace the kerosene with hydrogen. The graph on the left is a bit obvious, but we're looking at the total annual energy consumption of the distillery. The solid red bar at the start is if that was entirely met by kerosene, and then we're incrementally replacing in 10% increments that energy demand by hydrogen. And that sets the scene for the graph on the right-hand side. So we can see gravimetrically, if we replace kerosene with hydrogen, we have a lot less, because hydrogen is so much more gravimetrically energy dense, we need a lot less hydrogen to combust in the boiler to satisfy the energy demand. And of course, if you assume that it's green hydrogen or from a biomass source, potentially we have no CO2 emissions associated with that. So in a linear fashion, the CO2 emissions associated with kerosene combustion decrease as you replace it with hydrogen. Of course, that's not the whole story because we need to compress hydrogen to have any chance of storing it, particularly in an island environment. So if we look volumetrically, hydrogen is not very energy dense at all, and if we compress it to 350 bar, we still need an order of magnitude higher storage on a per annum basis than the amount of kerosene we would need. And that's no doubt why fossil fuels are showing so much preference. If we just have a quick look at the production process in terms of some energy and some waste streams. As I'm sure you know, you put milled barley or grist and water into a mash tun. That gets mashed and you produce wort. The byproduct of that is called draff and it's spent barley. So that usually goes off to animals to feed them, which is quite a nice use for it. The wort then gets fermented with yeast and we get CO2 produced in that process. To produce wash, which is about 8% alcohol by volume. And then that gets distilled in wash distillation to form pot ale, which is an organic, it's an aqueous byproduct with a rich organic phase in it and then a yeast fraction right at the bottom. On from the wash distillation, we distill the low wines and the offcuts from the previous spirit distillation. And the byproduct of the spirit distillation is spent lees, which is a lot clearer, as you can see. And the pot ale and the spent lees are just discharged to sea at the moment. But you can do things like anaerobic digestion, gasification, to get some kind of fuel out of it. Or you can even, for example, with the spent barley, you can pelletize it and burn it in a burner. Just looking at a waste stream audit, on a 5-week production period we monitored, we were getting an average of about a tonne of draff per mash. We have 2 production runs a day operating 5 days a week, so we're getting 10 tons of draff per week. And per run, we also get just over 3,000 litres of pot ale, just over 1,300 litres of spent lees, totaling 4,500 litres of liquid waste per run, or 45,000 litres per week. So that's all good stuff that we can kind of use and try and convert to hydrogen. And the method that we're using is this electrolysis of biomass. So it comes in 2 stages. First, you have the thermal digestion step. So we take a Keggin-type polyoxometallate catalyst known as phosphomolymptic acid. We dissolve that in water and add the biomass to it, and it forms a nice yellow colour. If we treat it using these reaction conditions, which are done anaerobically, we reduce the PMA catalyst, and we get left with biomass residue, and it's a nice colour change to blue. So that means we can analyse it using UV-vis spectroscopy or something similar to work out the extent of reduction and how much hydrogen and electrons we've actually extracted from the biomass. And then subsequently, we can feed that reduced catalyst solution into a proton exchange membrane electrolysis cell, where it gives up its protons and electrons. The electrons flow around the external circuit if you hold it at a particular voltage, and the protons diffuse across the membrane to the cathode where they recombine and you get pure hydrogen out. And the main benefit of this is essentially we can do this at much lower voltages than standard water electrolysis using this PMA catalyst as sort of a hydrogen vector. So we can then combust the hydrogen that we've produced in a boiler setup. We could electrochemically oxidize it in a fuel cell, which could then power a heat pump to deliver steam to the distillery, or we could use it to decarbonise the electricity site-wide. And hopefully this week we will have our initial results on that process over the next 2 days in Strathclyde. So just to wrap up, there we go. Almost on time. We've summarised the KTP project, given a review of the energy and waste streams, the annual energy requirements, and how we might substitute that for hydrogen, and we've introduced the electrolysis process. And as I mentioned, we're going to be doing some of that evaluation this week on the actual process itself. So a few acknowledgements here, and thanks for your attention, and welcome any questions.
Fantastic, thank you, Robert. That was fascinating and a nice insight into the whisky distillery industry, which I enjoyed. So any questions, please, from the audience? John.
What happens to the carbon at the end of it? Because obviously, so the question is, what happens to the carbon at the end of the process? Because obviously the biomass will have plenty of carbon in it.
Yeah, so there's obviously 2 stages to that process. There's firstly the thermal digestion step. We are set up to monitor how much CO2 is potentially released in that step, because we're doing it anaerobically, so anything that comes off should be CO2 at that point. The initial experiments we've done so far suggest there's not really much coming off at that stage, but I guess the biomass residue also comes out in that step actually, but we assume it's left as biomass residue within the solution, so we could filter that off and then recover the catalyst afterwards, so it's not being released as CO2 as far as we're aware. Whether that could then be spread as a fertilizer or something after we've exposed it to this acidic catalyst, I'm not sure. But yeah, so we can potentially get hydrogen from it. What happens to the rest of it, if it's not all completely digested, is an unknown at the moment.
But from what you're saying, it comes out, you're expecting it to come out effectively as a solid or a contained mass. It's not vented to the atmosphere, so you could do something
we could do something
fairly easily.
Ideally, yeah.
Okay. Yeah.
Nice. Yes. Just behind, thank you.
How much the voltage drop when you use the catalyst and without the catalyst?
So in terms of standard water electrolysis versus PMA, so in a standard, for example, a proton exchange membrane electrolyzer, because of the sluggish oxygen evolution reaction, you're looking at about 1.5, 1.6 volts, whereas in this we're looking at quite substantially less than 0.9 volts. So we're looking at less than 0.9 volts. But you also have to take into account there is a thermal digestion step at the start, which has an energy penalty. So what we're trying to work out is, is that initial step completely wiping out the energy benefit of the second step? Or is there a way we can actually use heat from somewhere else to fuel that step, power that step, and then it does become viable?
Thank you.
You're running all over the place. Thank you.
Yeah, thanks for the presentation. It's Paul Robb from Net Zero Technology Centre. So the question was initially about you'd given an emission figure for kerosene, and then Zero Waste Scotland had figured out a number as well that was similar but different. Did they use a life cycle analysis process, or was it as straightforward as here's some kerosene, we've got a conversion factor, and that's emissions?
I believe that's what it was, yeah. It was just conversion.
The latter?
Yeah, the latter.
So is the overall goal to be, well, net zero, or when you say decarbonise the distillery, is it to eradicate all emissions or to bring it down to an acceptable level?
Certainly initially, within the project timeframe, I think there's a lot we can do, because it doesn't make sense to just swap out kerosene for hydrogen, right? If there's pipes we can insulate, if there's stills we can insulate, if there's things like thermal vapor recompression we can put in to reduce the energy demand per litre of alcohol, we do that first, and then kind of whatever's left we can sort of consider to replace with hydrogen. Whether hydrogen's the answer, I'm not sure. There's certainly a role for it. Maybe in a larger island community context as well. We have a hybrid ferry, so it might be that we could do something with the liquid and solid waste, create hydrogen, which then powers the ferry as well. So there's lots of different ways we can do it. We're looking at heat pumps and electrical stuff as well. So we can potentially have electrolyzers in tandem with fuel cells, which run a heat pump with giving low pressure steam to the steam coils. So it's quite complex.
So that's why, for me, because of the complexity, what about... Sorry again, my name is Johnson, here at Watts University. So what about in terms of the economics of the entire process, do you think it's going to be viable enough because of the complexity? In
terms of installing an electrolyzer and all of that kind of stuff, it's a lot of money. There's if you look at some of the Bay's green distilleries feasibility studies, there's a good one by Locogen at the Arbeke distillery near Arbroath on the east coast of Scotland, and I think they're installing something like 1.7 megawatts of solar, 3 megawatts of wind turbines, 2 500 kilo hydrogen storage vessels, and a 2 megawatt alkaline electrolyzer. And that's coming in about 8.5 million to install all of that. And I think the government are giving about 3 million towards it. So, yeah. You could probably build a new distillery for that. So there's a big question as to whether or how much hydrogen can play a role in terms of the cost benefit and how quickly it will pay it back. That's not my decision. I don't have the money. But.
Fantastic. Oh, thank you very much. Thank you. Thanks very much, Robert. Nothing is without its consequences, is it? It's a complex system, so thank you. So last up, we have Ihai, so from the University of Glasgow, and he's going to talk about pore-scale imaging of hydrogen in porous media. So we need the storage. We need to make sure we can get what we put in, get back out again. So take it away.
Yeah. Hi, everyone. Think some different test. Okay. So my main research background focuses on the pore-scale imaging of hydrogen storage. How to do that? Let me think. In porous media, I'm Ihai Zhang, now a lecturer in geoenergy engineering from James Watt School of Engineering, University of Glasgow. Okay, so the first thing is why we need hydrogen storage. Okay, this is a big question. A lot of people already ask that because the hydrogen sometimes how do we generate hydrogen? Normally we can generate it from from renewable electrolytes from seawater and the storage in some place. People may decide we can store it in the tank or storage place, but actually the tank is limited space. So one idea is, because now in North Sea, around the offshore, we have a lot of the abandoned oil field. The people cost money to decommission this abandoned oil. It costs a lot of money, so we don't need to abandon it. We can use it as a big tank, there's a reservoir inside. And electrolyze the seawater, we generated hydrogen and storage inside. And this storage actually is a temporary storage. We don't need to long-term storage because we need to reproduction it. So here is the concept. So we store it inside the reservoir and later resell, reproduction it and use the ship to transport to the on-site and sell to the market. So for the hydrogen right side, we can see it's a little bit complicated than we think. So we have hydrogen top, and then we mix them. Also, sometimes we need a caution gas to keep the pressure, maybe use the CO2 or other things. And for the blue hydrogen, we can use the bio method to produce it, And so here, one side on hydrogen is very easy. It's similar like the CO2 storage. You have a lot of experience on CO2 storage, a lot of research on CO2 storage. Actually, it's totally different because for the CO2 storage, we needed permanent storage into underground, but for the hydrogen, we needed easy and high production rate. So capillary trapping is not desirable, and this is most of the trapping mechanisms inside the gas storage. However, very limited research has been conducted. So what do we do? So we can use the in-situ core flooding test and to see exactly how the hydrogen inside the rock sample, how it's injection inside, how it's the migration, for long-term storage. So here, on the left-hand side, this is the micro-CT instrument. So we have core holder, we have sample inside, and we have X-ray, have flat panel. The idea is we injection gas inside the saturate sample, and we have confining to pressure to give confining and receiving pump. And from this experiment strategy, we use the in-situ post-scale imaging. We use a different rock, the sandstone and carbonate rock, and we use the dusty flow rate because not in the underground, always the dusty flow rate and different pore volume injected. And also, we want simulated injection process and stop injection process and the storage process. We use the drainage test, imbibition test, and also storage test. So, the aim of the experiment is in order to see how hydrogen is trapping and moving inside the porous rock. So this is the main idea. So we conduct several experiments. So drainage, imbibition, storage, and so we compare the hydrogen with other gases to see what's the difference of the hydrogen. Is it unique or is it similar with such as the common gas, the nitrogen, because nitrogen always is a bench gas in the laboratory, and if it's the same, next time we don't use hydrogen because it's a risk to, and we can just use the nitrogen. So also hydrogen test with imaging with a different day to see what's going on. So it's very interesting since from full-scale imaging, left-hand side, the drainage test, we can see we use the same rock and same injection volume and same fluxion rate, and we can see the different saturation compare hydrogen and nitrogen. So hydrogen almost much lower than nitrogen. The reason, of course, obviously is due to the low viscosity of the hydrogen. And also after 40 pore volumes imbibition test, you can see the hydrogen only 11% of hydrogen still inside the porous media, but nitrogen still have a 36%. And also we storage the hydrogen for a little bit time. So here for 12 hours. So we still have the experiment for 1 day, 2 days, 3 days, 4 days, but still not sure on this PPT. But later, if you're interested, you contact me, and you also can find in our latest publication. So for the hydrogen, we can see what is interesting. After 12 hours, we can see some small bubble is disappeared. So, and for nitrogen, it's almost no change. So we quantify this process diffusion. Right-hand side, we can see what is more interesting. For the hydrogen pore volume, has the big pore distribution pore volume before storage, and then move on the right-hand side after 12 hours, become larger bubbles. Small bubble disappear, become larger bubble. But for nitrogen, it's almost no change. So why this happen? So we checked the literature. We thought it's due to outward ripening. Outward ripening effect actually has been invested more than 100 years, but people didn't pay much more attention on the current years on the gas storage. So afterward ripening is a diffusion flux of the dissolved gas. It can be from small bubble due to the higher local pressure, and diffusion to the large bubble. So here we have Henry's law. So we want to explain this phenomenon. So we got some little bit of calculation. We use the Henry's law, Fick's law, and Young-Plus equation. We combine this equation, and we can calculate one single bubble from small to disappear. How long it costs? So we cost it from the hydrogen. It's around about 10 hours. However, for nitrogen, for this calculation, it's more than 10 times slower. So that's the reason explained on the imaging why we can see the hydrogen small bubble disappeared, but the nitrogen is not disappeared in this time. We have more of these things. We also contact the contact angle to see how the contact angle changed before and after. So I have much more things. If you are interested, you can contact me later. So discussion. So it's a very interesting experiment. So we find that for hydrogen, it has nice trapping. Because it has a lower initial saturation, the trapping are in single pore. Pores not in multiple ganglia in the hydrogen. And once injection ceases, there's a tendency of gas become small ganglia, become large ganglia. So after a day, this large ganglia can disappear if a equilibrium with bulk gas in the appearance. So we found acetal ripening has been observed, and we need to relate the behavior to the theory and model things, because the current model, the current reservoir model, no model actually seriously think about the afterward ripening. And we found the buoyancy effect and capillary effect is very interesting. If small bubble, the capillary effect is not work, and then the buoyancy effect can move up. And for hydrogen storage especially, because the small bubble cannot be trapped easily inside the porous media. So further, we already booked the synchrotron experiment, and to see the dynamical change for the long time will be much more interesting. So the discussion, later, what's this application? Because this is a lab experiment, always from the mechanism thing to think what is the application to the engineering challenges. So we can find that from this experiment, maybe we can see less hydrogen can be trapped by the capillary trapping, and the hydrogen may auto-generate the large tank into the area of the underground. So it is making it much easier than we thought before to withdraw. So we maybe can get a higher reproduction rate than the current model. And from this experiment, we can also get a lesson that research should always focus on some of the small mechanism findings. That's because the small mechanism findings that give the engineering output. So the current model maybe didn't work and keep changes. So thank you for my co-investigator from in Imperial College London, Professor Martin Blount and Dr. Branco, and also thank you for the funding from Shirley to look program. And also, small advertisement. If there are any questions, you can send me the email. And so we have a strong team, University of Glasgow, for net zero energy. If you have any looking for the collaboration opportunities.
Brilliant.
Any question?
Thank you very much. Thank you. Perfect timing as well, so thank you very much. Any questions from the audience? Yes. Thank you.
Thank you so much, F. I think we already
discussed
your work earlier. But just a couple of things. First, like you mentioned, oil reservoirs as possible underground reservoirs. So are you focusing on depleted oil reservoirs or aquifers or depleted gas reservoirs?
That's a good question. So one side is because when the reservoir is abandoned, it means if it already had oil and gas production for a long time, years ago, and the aquifers underground aquifers that go inside again. So it's a lot of the brine inside, not the water inside. So this, you can see here, because there's only two phases, where is the water, where is the hydrogen. So assume it's an aquifer, underground aquifer, but in the future, maybe three phase, we will add some the residual oil still inside to see what's going on. Yeah.
But then obviously the wettability effect would come into.
Yeah, that's right. Yeah, we also have an experiment to test the different wettability. So we should show the oil wet rock, how it is trapped to the hydrogen, and this is the opposite is water wet rock. Yeah, right. Yeah.
The other question, when you said about oswald ripening, so when your bubbles are disappearing, so does the saturation still remain the same, or?
Yeah, this is a good question. For actually, because the experiment for the CT scanning, you can only see in the middle of the part of that. You cannot see the full sample. For in our case, for the hydrogen, the saturation is a little bit slower, little bit, but it's on the reasonable the error rate. For the nitrogen, it's totally no change. Yeah.
And also, like, why do you just see hydrogen on one side? Did you have any other thoughts on that? The hydrogen is just on one side, right, in the rock sample?
Yeah. So it's one thing to make heterogeneity, or I think the injection hole something, because the injection is not exactly in the middle.
So it found a channel and then it just.
Yeah. When they found a channel, they always go that channel. They never go in the other side because it's easier to move. That's one theory. The next time you will try to inject another side and to see if it's still going right side or not. That's a lot of interesting things.
So you do drainage emission both from same side or opposite sides?
Same thing.
Same side.
Yeah.
Thank you so much.
Mm-hmm.
Yes. Thanks.
Yeah. The hydrogen storage has been a thing that kind of accepted to be challenging because of the atomic size of hydrogen is small.
Yeah.
So there is this discussion that even in the pipeline that is traveling, it can diffuse.
Yeah, it can run anywhere. That means, yeah.
So I was just wondering, what benefit are we now going to have having to produce hydrogen and then send it back to oil reservoir to store it?
Yeah, that is a good question. Someone asked, why you electrolyze hydrogen and then use it? Why you didn't not directly use the electrolyte to electrolyte car or anything like that, right? This is because in the wind farm, we produce the electricity. We cannot control sometimes the wind is very strong. It is extra electricity. So this extra electricity, we can use it to electrolyze the seawater and get hydrogen. Then because sometimes it's a very strong wind in the winter, sometimes in the summer you cannot sell the electricity, so we can just generate the hydrogen. Then generate hydrogen normally in the offshore, no space to storage, it's a limited tank. We just use the abandoned oil field. That is just a concept idea.
Wishful thinking.
So I was wondering, because if you would try and see what is your imaging on the metallic storage too. That is not a question, but since we are also aware that if you send in the metal that hydrogen can also diffuse from metal, maybe if you extend your research today, you can answer some of this storage question.
Yes.
Do you have a question?
All right. So I'm just wondering if you think in future there's going to be competition between some of the depleted reservoir that we can use for CO2 storage and the ones that we can use for hydrogen storage. Or are there peculiarities? So we have those that will be suitable for hydrogen storage and those that will be suitable for CO2 storage.
Yeah. Actually, this is a good question. Because in the real practice, some ideas about injection hydrogen and CO2 together into the underground, because the high CO2 can be a caution gas to inside reservoir. And the hydrogen, because it's very low density, it can then move to the top, to the cap, near the cap rock, and the CO2 in the bottom. And the CO2 can be high pressure, high density, and it goes downstairs and stored inside, and we can just put reproduction hydrogen inside the top of the reservoir. That is one idea for injection together to protect. Also, the CO2 can turn around to protect the hydrogen to run away other place. Yeah, but it's never been practiced, so no one knows it works or not. Okay.
Fantastic. Any other questions? Oh, John.
Yeah, so when you have
Thank you. So you said that if you have a depleted reservoir that's then been re-pressurized with brine, at least partly, is the hydrogen density and pressure going to be enough to displace the brine again? Or, and the next part of that is, if it is, then does it displace back into the atmosphere, aquifer, or does it do you just have to produce the brine to get it out of the ground to create the space?
That is one thing. So we also, the experiment, that's why we inject and you use the drainage and inhibition test to simulate the injection gas and then the other side, and then gas come back when we close that. So the idea is, of course, the injection pressure, or during the injection process, always higher than the blood pressure. So we can, if it's not higher, we cannot go inside and cannot inject inside. If that is higher, and this can be recovered from the water. The more we move outside, this idea to move still in the reservoir. We increase the reservoir pressure, or we use just recovery to the other place. Yeah, and then when we close the stop the injection, the water will come back because there's some hydrogen will that dissolve inside the water and get back. We can see, like the well testing, we can see the pressure drop.
Thank you. Any other questions? Nope.
Nope.
Okay. Thank you very much.